Here's a really interesting physics problem which is almost thermodynamics all the way, but not completely, and it may not actually be obvious at first glance that it is a thermodynamics problem. So here's what we're dealing with. The question starts by saying that we're dealing with a spaceship which is at rest on Earth, and then the barometer. So inside the spaceship, there's a barometer which shows the atmospheric, well, which actually shows the pressure inside the spaceship. And one of the assumptions for that to happen is that the spaceship, and I'll write that down, so the spaceship is sealed, okay, which is what you want to be the case if you're launching the spaceship to space, obviously. You don't want any leaks or anything to happen. So the barometer inside shows a pressure given by 750 millimeters of mercury. Now, during takeoff, so the spaceship is no longer on Earth, but it's taking off. During takeoff, which occurs with an acceleration of 9.81 meters per second square. So it seems like the acceleration of takeoff is the same as lowercase g, right? Is the same as the gravitational acceleration at the surface, which is this. So during takeoff, which occurs with an acceleration of a directed upwards, the barometer now shows this new height of the mercury. And the question is, by how much did the absolute temperature increase inside the spaceship? So it sounds a bit weird because it sounds like it's a fluid mechanics problem because we're dealing with barometers and maybe there's a bit of mechanics involved with non-inertial frames of reference because the spaceship is accelerating upwards. And then all of a sudden, the question hits us with what's the change in temperature. So let's actually think what's happening. What we're dealing with at the beginning is a rocket which is, now this kind of looks like a cartoonish kind of rocket, but it serves the purpose, which is to, just have a basic drawing. So this is the rocket on Earth. I'm not going to draw the Earth, but I'll say that initially there's zero acceleration going upwards. Now, inside the spaceship, there's a barometer, and the barometer shows the pressure inside the spaceship. So the barometer looks something like this. You have a tube, and then you have around the tube. So you have this tube which is submerged in something like a tank of mercury, and then the mercury raises up through the tube, and this height here tells us what the pressure is, right? So we're basically doing what we call like the horizontal line test. So we draw a horizontal line which passes through the same liquid, and we'll have that the pressure here at, let's say, point 1 is going to be equal to the pressure here at point 2. And that's going to give us the atmospheric pressure, the PATM, or the atmospheric pressure inside the spaceship, or just the pressure of the air inside the spaceship. Okay, so I'm gonna drop this subscript and I'm just gonna call this just P. So what we'll have is that our pressure will be rho times G times H. So this is the pressure of the air inside the spaceship when the spaceship is not actually traveling upwards. So the pressure is given by this thing here, right? Which is density. Now this is density of the mercury, which is, let's actually put a subscript Hg. So rho Hg is 13,600 kg per meters cubed. G is obviously, it's this G here, 9.81 meters per second squared. And then H, so the first H that we're using is the one when the rocket is stationary. So this H is 750 millimeters, right? It's literally this height, 750 millimeters. And this gives us, the pressure inside the spaceship, but we're not actually going to put in numbers yet. we're gonna do that later. So now let's actually look at what happens when the rocket starts traveling upwards, when the rocket starts taking off, basically. So we still have the same rocket, which is still sealed, and this is the fact that the rocket is sealed is key, as you'll see in a moment. So we have the rocket, kind of draw it in the same way, and then we have the tube, and then something happens now. So first of all, there will be an acceleration going up of 9.81 meters per second squared, and now we still have the same uh, mercury bath, if you want to call it this way, and then inside the mercury bath we have the tube, and this time the amount, the level of mercury inside the tube is different, so it only goes up by this much, where and this much means H prime, where H prime is 412.5, so 412.5 millimeters. Okay, so I'm gonna write what we know and then we're gonna try to justify why some things happen the way they do. So we have this new height and we have this new acceleration. But according to fluid mechanics, this horizontal line test must still hold, right? So the pressure here must be equal to the pressure here. So the new pressure inside the cabin, let's call this P prime, which for some reason has changed, is still equal to the pressure due to that column height, and that is given still by rho, by the density of the mercury, because it's the same fluid. But now we don't actually multiply this with g, or we don't just multiply this with only g, because if you think about it, the rocket is a non-inertial frame of reference, which means that because it's accelerating, everything inside the rocket is heavier, including the mercury, right? It's like when you go up with an elevator, you become heavier. So in the same way, this mercury here and this mercury here will become heavier. So this is not multiplied by g, it's going to be multiplied by g plus the acceleration. So g plus acceleration, this is going to be sort of like g prime, also known as the apparent gravitational acceleration. Gravitational acceleration. So everything becomes heavier, including the mercury, and the new pressure given by the barometer is given by this G prime. And then it's again multiplied by H prime, which is the new height. So the key difference here was the fact that in the second case, when the rocket is taking off, we don't use the same G. Instead, we use the new G, the G prime, which works for this non-inertial frame of reference, which is accelerating, which is G plus A, basically. Okay, so we're dealing with the air inside the rocket, which at first, the air had a certain pressure given by this formula, and then the pressure changed, and the new pressure is given by this formula. Now, we also know that the rocket is sealed, and if the rocket is sealed, it means that the volume of the air inside is constant. So it is constant, which means that we're dealing with an isochoric process. So among everything that happened, like among all the fluid mechanics and all those non-inertial frames of reference that we looked at, there was an isochoric process hiding in this problem, which, the clue to that was the fact that there are no leaks going out from the rocket, which makes sense if you think about it. So if we're dealing with an isochoric process and the pressure changes, which it does change, the other thing which has to change is the temperature. And this is why the question is asking by how much the absolute temperature increases, because an isochoric process is given by P over T is constant. So if we use this, we'll be able to find what happens to the temperature. So let's write this as follows. So we have P1 over T1 is equal to P2 over T2. Now, what does 1 and 2 mean? Well, 1 is simply when the rocket is stationary, rocket is at rest, let's call it, and 2 means when the rocket accelerates. So that is given by, the second scenario. So what we're trying to find is not T2, but rather T2 over T1. So if we rearrange this equation here, we're going to end up with T2 over T1 equals P2 over P1, which is equal to, and now we can substitute. So instead of P2, I'm going to write this. So that's density of mercury times G plus A, and then times H prime over, and this is rho mercury G times H. And now some stuff cancels out, so those go away, and then we end up with G plus A over G, H prime over H. So T2 over T1 equals, so this fraction becomes 1 plus A over G times H prime over H. Okay, and now we just put in the numbers. So we have 1 plus, now A and G are equal to each other. The values are equal to each other. So this is just 1 multiplied with 412.5 over 750. So this is 2 multiplied by, and this should be 0.55. And the answer is 1.1. And that's it. So this is how much the temperature increases inside the cabin, right? So the temperature increases because the pressure also increases, and they are related to each other through this isochoric process, which happens because the spaceship, the rocket, is sealed from the outside. And that's the end of the question.